Okay, welcome everyone to this Quantum Wednesday. We have James Wootton from Moth Quantum. I think that's the startup based in Switzerland, right? And he's going to be talking about his paper, or I guess the paper that you all worked on at Moth Quantum, quantum
Mm,
circuit design via dynamic Pauli constraints.
yeah,
Um, yeah, I had a look at the paper and it looks very interesting. So I'm curious. Um, the floor is yours.
thank you. So I will just do my screen share. We did do a check earlier, so I don't anticipate anything going wrong, but shout at me if you can't see anything. So yes, thank you for coming. I'm going to give you a talk which I retitled today because it seemed like it was a better name, Generating Game Levels on QPUs. So it's focused around the talk that Farouk mentioned, sorry, the paper that Farouk mentioned. But it's also the origin of that paper and how we're using that paper and how we hope other people will use that paper in the future as well. So it turned into quite a broad overview. But yeah, that work was done by me, but with my colleagues Merlin, Daniel, and Pierre, who are fellow researchers at Moth. Okay. Let's get into it. So first, I thought I'd just say who I am. I'm one of these people that came into quantum computing the boring way of doing a PhD and then doing a postdoc and then blah blah blah. I've been in quantum computing 20 years now. But one thing that is atypical about my journey is that 10 years ago, well, at that time I was a researcher in quantum error correction, and at that time, typically the thing you mostly did was study decoders on the surface code, and we would simulate surface codes with hundreds of qubits, and we'd call those small versions of surface codes. And yet in the lab, they'd had one or two qubits, or five at the very most. And it seemed like such a disconnect between what we were thinking about theoretically and what was actually being done in the lab that I kind of got bored of researching sci-fi and wanted to do something of more direct appeal and impact to the taxpayers who were funding me at that time. That was during my PhD at the University of Basel. So I took a year and got some funding to make a citizen science game which was called Dikadoku. And because in 2016 I was already in this mode of thinking about outreach and thinking about the public and thinking about games and thinking about quantum, that was when cloud quantum computers arrived. And so I immediately started thinking, well, what can I do for cloud quantum computers with games? And so I made the first game to run on a quantum computer, which was a version of rock, paper, scissors, basically. I then soon went to IBM Quantum, where I was doing education and outreach still, but also research. And within that research, I was still wanting to answer this question of what can quantum computing do for games? When we're talking about citizen science games or outreach games, this is games doing something for quantum. It's games educating about quantum games, um, demystifying quantum. And if you look at the history of computer games, the first computer games on classical computers were also about what can games do for computers? How can it educate people about programming? How can it give us insights into human computer interaction? But what is really interesting, I think, is to turn it around. What can quantum do for games? So that is some work that I did at IBM Quantum. And as a result of that, Moth was founded, and as a result of some other things. It wasn't just me. Um, and that led to me joining Moth and continuing that research from 2024. But what is Moth? I hear you cry. I don't actually hear you say that. I haven't got any spying devices in your house. So, who is Moth? Well, there are many quantum computing startups at the moment. Some of them look at what quantum can do for finance, or what quantum can do for healthcare, or what quantum can do for logistics. And they're all great. But we are the only company that is focused on what quantum can do for consumer applications, such as games, but also things like computer graphics or visual arts, and also music. So we're a company that does research. We're a company that builds products, and we collaborate with creative people because there are creative people already interested in this field, engaging with this field. They don't care about quantum advantage. They just want something new and unique. And so you can start building products that are useful for people even before you have to hype up your quantum advantage. Now, I think I just saw a message come in the chat. So I should say if people want to ask questions, that's fine to ask throughout. I'm only on one screen though, so I'll ask someone to read them out if there or people can ask themselves if there is a question. So feel free to interrupt. But yeah, the final point on this slide is that our headquarters is in London. Our research is mostly based in Basel, and our engineering is in New York. So we have three major offices in these three geographies. So one thing I want to say early on is that we're not one of these startups that likes to do things in secret. We want to be out there building things with the world. We want to engage with open source projects, make our own open source projects, do things in open source as much as possible, have tools that are open access, have people come and collaborate with us. And part of that is that we're making a Discord. It's not currently very active because we're only just spinning up the Discord and we're only just spinning up our new platform. But if you want to be there from day zero, pretty much, then join this link and go over to our Discord. Okay, so let's start the story that this talk is about. And this story begins, well, in 2019, actually, the end of 2019, but I'll call it 2020. So 2020, I worked at IBM. IBM, we had this, I think it was a 64 qubit device called, no, sorry, I can read the numbers on here. Was it a 53 qubit device called Rochester? So if you have a 53 qubit device, what do you do with it in 2020? So at the time when we had tens of qubits, we don't really know what to do with them. And back then, it was too much to expect a quantum advantage. You didn't have people going claiming quantum advantages all the time. So what did you do back in 2020? Well, one thing that people often used to do was do few qubit proofs of principle. They would think, oh, okay, I want to do this financy thing on a fault-tolerant quantum computer. Let me imagine a 5 qubit version of it. I'll do it on our current hardware. Then we write a paper and say, here's a thing we want to do in the future. We already did a version now. Aren't we clever? And of course, if it's 5 qubits, you can do it with your phone. So you don't really need a quantum computer, but it's a step in the right direction. Another thing you could do back then is take the whole QPU and use it to just do a thing, to show that it works, to show that it performs a task. And you don't think about it being a quantum advantage task, you just show it works as a computer. It's not an oversized science experiment, it's a computer. Now the mindset is more towards everything has to be a quantum advantage claim. I'm not a big fan of that, to be honest. And I think the creative space is perfect for not having to make quantum advantage claims because people find the things useful even without quantum advantage. So you can work towards it and cherish your QPU for what it is and not pretend it is something that it isn't. But anyway, that's a rant for another time. So what did I want to do with the QPUs of the day? Well, two things. I had a background in quantum error correction. Still like quantum error correction enough. Not enough, sorry, a lot. So one thing that I did was run proof of principle and benchmarking protocols based on quantum error correction. But the other thing I did, and the thing we're talking about today, is procedural content generation. So, what is procedural content generation? It is the algorithmic generation of content for games or for graphics for other media. So, that could be generating the map that you play Civilization on. It could be generating the world that you are going to go and explore in Minecraft. It could be generating the next planet you visit in No Man's Sky. It could be generating a puzzle when you're playing a puzzle game. It could be generating the texture on a teapot when you are rendering a CGI movie. And in fact, um, one of the really fundamental algorithms for procedural content generation did win an Oscar because it was useful in CGI. So it's just the algorithmic generation of stuff for use in media, basically. It's a very broad church. Um, so sounds fun, but why quantum? Well, if you want to have a bit of an idea of why and how we can use quantum for procedural content generation, here is a paper you can go and look at. I'm going to be giving these archive screenshots for all of the papers that I'm talking about during this talk because everyone's got access to the archive, so it's a great place to go and get papers. Most of them are published in various places. This was published in the proceedings of uh, a conference in game design, which is where people publish things in the academia around game design. But you can go and check that out for more detail. But for the story that we're focusing on here, why would you use quantum for procedural content generation? Well, in the long term, you can use it to do optimization and constraint satisfaction. So procedural content generation is essentially you want to make a thing, and so you're wanting to make, say, a level of a game, and you want that level to be the right hardness. You want that level to not have game-breaking bugs. You want it to satisfy a bunch of constraints, and you want it to be optimal according to a bunch of um, cost functions. So ideally, the perfect thing to do is to solve those optimization and constraint satisfiability problems, but those are hard. So you don't do that. You work around. You find workarounds, you find cheats, and those cheats mean that procedural content generation is typically not like the content you generate is typically not as engaging as you might want, and it seems very samey after a while. If you've seen it, so Perlin noise was the thing I half mentioned earlier, the algorithm and that won an Oscar. If you've seen more than 10 maps generated by Perlin noise, you look at them and say, that's Perlin noise. They stop being, oh, what a nice map. And you see behind the curtain and they're not so engaging anymore. To keep on being engaging, to be truly engaging, for PCG to be as good as it could be and as useful as it could be, you need to solve these hard problems. So we have reason to believe with algorithms such as DQI that we would be able to tackle these with a quantum computer in the future. So that is the sort of long-term reason to think that quantum computing will be useful for procedural content generation. But what about the short term? In the short term, you have a bunch of qubits with a coupling map, and mostly what they are going to do is be some qubits. They are going to have some quantum dynamics. They're not going to be running what's it called, a Fourier transform or something highly abstract like that. They are just going to be a bunch of qubits interacting according to quantum dynamics. So in the short term, can we find ways to use that as part of a generative process? And that is what my work in 2020 was about when I used it for map generation. So I've noticed a few things popping up. I'm going to have a quick look. It's people sharing links. Nice. That's yeah. One thing about the archive these days, if you'll see from these screenshots, is that they don't have the actual code on them anymore in the screenshot. It's what privatization does, you know. Capitalism makes everything worse. Anyway, again, a rant for another day. So, if you are going to take a quantum dynamical process and do it and say how great it is, well, if you're doing it in the context of something like quantum chemistry, then it's very easy to do because that's exactly what people like. If you want to look at quantum magnetism in an Ising model, it's very easy to do. That encoding is obvious. But if you are going to take quantum dynamics and use it for quantum procedural generation, then the encoding is not so obvious. You need some way of encoding a problem that you care about from the context of procedural generation into a bunch of qubits, such that the natural dynamics of those qubits are useful to you. So I embarked upon a project to do procedural map generation, so geopolitical map generation. And I decided the best way to do that was to let qubits be AIs, essentially, governing a a civilization-like game. So there would be a game. It wouldn't be a game for the player to play. It would be a game in theory, in a sense, that the algorithm plays to generate some content. Um, but we would use it's a game in which there is a bunch of countries, and those countries are interacting with each other, and those interactions are going to cause different cities to rise and fall. They're going to cause the borders to change locations, and it's going to generate a geopolitical map with cities, with borders, and with a history behind it. Because that kind of content is useful in various games like Dwarf Fortress or Caves of Cud. These are games that are highly dependent on procedural content generation, and they generate a world, and that world doesn't just look like a world. You go inside it, you go around talking to the people, you discover the culture of the world, and it's got a history to it. And that was all generated during the loading screen. It's that kind of map that I want to be generating. So how am I going to use qubits to do it? So the encoding is essentially, I very much summarized on this paper, but you can check out the paper for more details. The um, the encoding is you've got a block sphere. That block sphere has three coordinates, the x coordinate, the y coordinate, and the z coordinate. And we are going to basically map these to three parameters. How aggressive your country is, how defensive your country is, and how much it doesn't want to do either of those things. It just wants to go off and explore and do science and stuff. And there are constraints on this. A country cannot spend all of its resources on everything. It has to prioritize different things. And so that natural constraint within the game is mirrored by the constraint on the block sphere that x squared plus y squared plus z squared cannot be greater than 1. So you're taking a constraint that ex should exist within the game that you have to share out resources, and you map that to a constraint that exists within qubits on the radius of the block sphere. Also, once you've decided whether to attack or explore or defend, who are you attacking? Who are you defending against? That depends on the relationships of all of the other nations. And so those relationships are being encoded on the two qubit correlations. And again, there are constraints here. You can't, or at least shouldn't, be at total war with everyone. You don't have the resources. And that is something that is, in a way, reflected by something like the monogamy of entanglement. Uh, So the monogamy of entanglement means that once you're very correlated with one qubit is very correlated with another qubit, it cannot be fully correlated with other qubits. So this is a way in which I have found an encoding of the where you put your resources as a very simple model of a government in a very simple civilization-like game, and map that to the natural constraints that are present in a set of interacting qubits. So then what we come to is that, as I said, the qubits are used as a simple AI for this game. And what it corresponds to is that so you have a circuit and you do a tomography. You measure the X expectation value, the Y expectation value, the Z expectation value for every qubit. You measure the two qubit expectation values for all pairs of neighboring qubits. You look at those numbers and then you use them to determine which move each nation is going to do. If you've got one nation which is all the way up on attack, it's going to attack one of its neighbors. And you look at the two qubit correlation functions to find out which one. If it's all on defend, it's going to defend against one of its neighbors. And you look at the two qubit correlation functions to determine which one. If it's explore, it's going to do a move that increases its territory in the direction no one else is. Um, so it uses these expectation values to determine what move it's going to make. And then these moves are applied within this simplistic civilization-like game. And then once you've applied the moves, you see what happened. Who has gained a city? Who's lost a city? Who has gained territory? Who's lost territory? Based on that, you then apply gates to change the state. So if you're a nation that has lost a lot of territory, then you should apply a gate which is going to increase your defense. It's going to put you increase your X expectation value so that when the next move comes, you're going to defend and you're going to prevent losing more territory. So you apply gates which change everyone's strategy in a way that makes sense. And then you go back to the start. And throughout the process, you're changing everyone's strategy, but all of these changes are not necessarily consistent with each other. They are going to be ruled by the natural constraints of the qubits, which correspond to constraints that make sense within the game. And therefore, you're going to get some quantum dynamics building up over time, influencing the dynamics of the map, but influencing it in a way that actually makes sense. Okay, so what was the output? Well, these are some of the maps that I generated. These are the maps that are in the paper. If you think they look a bit AI, look in the paper at my terrible color scheme, and you'll see why I asked an LLM to give them a quick scrub up. But these are the maps that I generated through the quantum process. So it works. Could we do similar classically without any need to do any QPU stuff? Absolutely. But the point was that in 2020, a QPU did something real and useful. It did a process of procedural content generation and proved that quantum computers at that time were arguably computers and not just oversized science experiments. But also, and you'll see this in the paper, it was benchmarked against a random player. So, because yes, it makes a nice map, but could a player acting randomly also make a nice map? So we have to show that it is acting not just randomly, but it was also acting intelligently. It's acting in a way that, or strategically, acting in a way that actually um, works strategically. So for this, one of the nations was singled out, um, and in some runs was run using the standard process in which you look at the expectation values, you determine the move through that, and then you add in gates, which changes your strategy. And in some trials, one of the qubits just was random. And what you found was, so then I looked for each nation, how big that nation was, how big that country was, how much area it had as for each step of this algorithm, which are here called years, but it's just each move in the algorithm. And really the aim of these nations, the aim of the player, whether it be random or QPU controlled, is to increase the area of its nation. And of course, it always increases over time. But what we find is, on average, the QPU controlled nations um, increase their size notably faster than the random ones, which is showing that it is behaving strategically. A 2020 quantum computer can control a nation perhaps better than some modern governments. Okay, so again, a rant for another time. So I've gone through this very quickly, but um, it's worth talking a little bit more about a part that I glossed over hugely, which is to say, oh, if you're losing territory, you better make a gate which increases your X expectation value. That is not how we usually do gates. We usually do gates by saying, please do a Hadamard. And in this case, the Hadamard will take you from fully attack to fully defend. But if you're not at full attack, if you're full explore, if you're already at full defend, the Hadamard will do something very different. So, how do we actually do this part five? Apply gates to change state. Well, if you look at the actual code behind it, what I had was these commands get block and set block, get relationship and set relationship. What get block is doing is it is, well, okay, and update tomography. So update tomography is happening often. So the SDK, let's call it, that is running this game, knows what all of the single and two qubit expectation values are. What get block does on a particular qubit is telling you what um, those expectation values are. And then what set block is doing is you give a target and you say something like, I want the X expectation value to be +1. So then what set block does under the hood is it says, okay, what is the X, Y, and Z of this particular qubit? So it's this point on the block sphere. I want it to be, I've been told to put it here, and then it figures out the gate to do it. So it means that at the level of the user of this SDK, essentially, they're only thinking in terms of, I want to see what these variables are, and I want to command what they should be. And they're not thinking about what the actual quantum gate is, whether it's a Hadamard or an S gate or whatever. So it's essentially a different way of conceptualizing quantum computing, a different language for quantum computing, in which you're looking at single and two qubit expectation variables as variables and uh, giving commands by saying what you want them to change to, rather than thinking in terms of standard gates. But under the hood, it's all just standard gates. Similarly, get relationship is saying for these two qubits, give me the two qubit expectation values. And set relationship is saying something like, I want XX to be equal to +1. And, and then it figures out a gate that does that under the hood. It's a little bit more complicated because you've got to think a bit more about what you actually mean by that in the case of a two qubit state. If you're saying just XX equals +1, that doesn't fully specify what the state is. So what do you do about all of the other expectation values? Maybe you should keep them the same if you as much as possible, which is actually what is done in this. But it's basically, and then update tomography is a thing you have to do every now and again. You can't say get block, set block, and then set block again without updating your expectation values because it will just get it wrong. When it figures out what gate it has to do, it does that using what it knows the expectation values to be, and to update it, it has to find more expectation values. So this is basically the interface that is running underneath this map generation process. So what I then did is think, well, this can be used for more than just map generation. It's a general way of thinking about hybrid quantum classical computing, where instead of thinking about state vectors, we're thinking which is a quantum set of variables. We're thinking about expectation values, which is essentially a classical set of variables. We're thinking of the quantum computer as a big bag of expectation values. These are our variables. We are going to then tweak them and look at them again and tweak them and look at them again. And that's going to be the sort of flow of our process. So to think about this further, I extracted all of this kind of interface into its own open source package, which you can find, well, its original home is on the Qiskit community organization, but it's now being continued development is now in the Moth organization GitHub, and it's called Quantum Graph. Why is it called Quantum Graph? I can't really remember. It's quantum, and you very much have to think about the coupling graph. I think that's basically it. I don't really like the name anymore, but that's what I called it. So there you go. So it's basically a way of creating utility scale circuits native to a device's coupling graph. It worked in 2020 on Rochester, and it's something we can still apply today on IBM Miami, which is the 120 qubit device, and also non-IBM devices. I don't work for IBM anymore. Other quantum hardware providers are available. Quantinuum, for example. Also, another thing to mention is that sometimes you might be doing some targets that are mutually inconsistent. You might be saying, I want this qubit to be in the Z equals 1 state, and I want uh, these two qubits to be in the XX equals 1 state. And those two things aren't consistent. Now, this is also a thing you get when well, this is a bit of a spoiler for what's coming, but this is also something you might get when you've got a Hamiltonian, and one term in the Hamiltonian says point in the Z direction, and another term in the Hamiltonian might say align these two in the X direction. It finds a compromise. So in quantum graph, the way you find a compromise is that when you say set relationship, you don't go all the way at once. You just go a little step in the way, and then you go on the step in the way to for one of your inconsistent other targets that you have, and then you alternate between them, and it's like a trotterization where the evolution as a whole moves towards a compromise. Okay, so now let's use it for something else using 2026 hardware. And what we did is use it for level generation in a horror dungeon crawler inspired by the Backrooms lore. So this is our trailer video for that. You can play it in both in a top-down mode, as you can see on the screen now. It's like a horror Pac-Man, or you can play it in this mode, which is in 3D, which is like you know, Backrooms Doom. In all cases, the levels are generated on a QPU. So you can go and check it out now, backrooms.mothquantum.com. Um, but I will tell you now how the levels were generated. Basically, we the the basis of it is as an Ising Hamiltonian or an Ising Hamiltonian, if you want to pronounce it correctly. So you've got a bunch of qubits there, and you think of ZZ interactions, and you want some of those ZZ interactions to align and some of them to anti-align. And you just use the Ising Hamiltonian as a way of drawing out a level. So the levels are you walking around uh, a bunch of rooms, and those rooms either have openings between them or they have walls between them. And so the way you draw out the walls you want in your game is to set the corresponding uh, relationship between two qubits to uh, anti-correlate, and if you want an opening, you set them to correlate. So the Ising Hamiltonian is just the way in which you draw out where your walls are. And so the reason why I've got this screenshot from the game on top of the QPU is because it's very much that like you've got this qubit here and this qubit here. These are anti-correlated. That's why there's a wall. These two are anti-correlated. That's why there's a wall. In fact, this qubit is anti-correlated to all of its neighbors, but uh, this qubit, for example, is correlated with all of its neighbors, and so there's no walls. So that's so we start off in the all plus state, which is essentially the superposition of all possible wall placements, and then we use quantum graph to drive it down towards the ground state of this Ising Hamiltonian. So in the most boring case, what this is going to do is it's just going to reach the level that you have designed, and then you get the level you've designed. But you didn't really need a QPU for that. So what the QPU is giving us is that we don't actually want the level we've designed. We want the level we've designed to be a template, and we want variations on that level. And so we're using the quantum process to generate variations of the level. And so it goes towards the ground state, doesn't get quite there, and therefore it's going to be generating variations on a template level. This allows us to sort of um, design a progression of levels in the game, so we know pretty much what people are getting, but it also allows it to be fresh and new every time. Now, it's true that one of the bad things about procedural content generation classically is often you are generating um, variations on a theme rather than doing something really new and engaging. But again, new and engaging requires us to solve problems that would require a fault-tolerant quantum computer. So until we get there, we're not claiming quantum advantage. We're just doing ever more sophisticated tasks with a quantum computer. That was the wrong direction. So we ran this on IBM Miami, which is a 120 qubit quantum computer. And we use a mixture of emulation and the real QPU. So for this iterative process of going a little bit towards the ground state, redoing the tomography, going a little bit towards the ground state, redoing the tomography again and again and again, this builds up the circuit that we need that will get us towards the ground state. And because expectation value simulators are very good these days, we use an emulator, so a simulator, to do that iterative process and quickly build up the circuit that we need to get close to the ground state. And then what we do is run that on a QPU to do what the emulator cannot do, which is sample from different bit strings. Uh, and the reason why we want to sample is because the levels aren't built from the expectation values, they're actually built from the bit strings. And we want to get this effect of sampling from different bit strings that come from the QPU to make the level shift as you walk through it. Because this is a big backrooms thing. To be honest, I don't know everything about backrooms lore, but you go into this world, this weird horror world, where you're stuck in um, very bland looking office, but it's constantly shifting around you. And so we can take this element of the law that has already been built up on this internet phenomenon and connect it with quantum superposition by using superposition to actually provide this shifting environment. And we use samples from the QPU to do that. So this is arguably the first full quantum game. So remember, the first person who is telling you that is the person who made the first game on a quantum computer. So whatever the first game on a quantum computer is, I can claim to have made it. But I'm claiming it for this one. This is the first full quantum game. And how do I define a full quantum game? Well, there was a paper a few years ago by Laura Piispanen and various other people, including me, um, that looked at all of the games that people have made that are arguably quantum games. So things that I've done on actual quantum computers, things that other people have done as citizen science projects or outreach projects, things that people have done just quantum inspired by quantum, and found that there are three dimensions of quantumness that are relevant when people claim to have made a quantum game. One is games that use quantum inspired mechanics. So, very classic example of this, or examples of this are quantum chess and quantum tic-tac-toe. These are normal games, but quantum. Uh, the normal rules are supplemented by quantum inspired rules, like you can make a move in superposition. Um, there are other games that are useful for quantum research, so such as my old citizen science game Decodoku, where you're inviting the public in to help you do research by means of a game. And there are also games where there is a component that is powered by a QPU. I won't say run on a QPU because you don't want to be calling a QPU every frame. That would be crazy. But with some component that is powered by a QPU. Uh, Typically, I'm the one who focuses on the last one. Um, but Quantum Backrooms is the first to satisfy all three of these. Because we are using the samples to make this shifting environment, it's got a quantum inspired game mechanic. Uh, because the level generation runs on a QPU, it's powered by a QPU. But also you can compare the expectation values you get out of the QPU to the ones that you expected from the emulation to get a sense of how much noise is affecting things. I actually realized I wrote these things on the next slide, so I should go there. Yeah, but I thought another aspect of that, and one that I work on in another project called Quantum Awesomeness, which I'll talk about in a moment, is that it also gives the player a way of experiencing a QPU. If we made levels on every QPU, and it allows the public to get a sense of how one QPU differs against another. Because if you play one QPU and it feels like playing that game gives you a really good game experience where the levels have been well designed, then that suggests the QPU is doing what it should be doing, providing variations on the levels that you've designed. If another QPU is just complete random nonsense all of the time, that's a bad QPU. And there's also a one-to-one correspondence, as we saw in this image here, between the level and the device. So if you were to walk as the player over here and you find over here it's complete random nonsense, then you've discovered, oh, that corner is complete random nonsense. So it gives a quite visceral and accessible way of the public giving a benchmark, as well as also providing us with more qualitative benchmarks. So this is why I would argue that Backrooms is the first full quantum game. Uh, Now I'm got 15 minutes left, and I still haven't got on to the bit that involves the paper that this is actually supposed to be about. So let's move towards that. So one thing about quantum graph is it's quite similar to another um, project that happened around the same time, which was an algorithm for quantum imaginary time evolution by Mario Motta and a bunch of other guys. So they are basically doing trotterized quantum imaginary time evolution. So quantum imaginary time evolution, if you don't know, is you've got a Hamiltonian. That Hamiltonian has a ground state, and you want to push towards the ground state. So rather than processing around the Hamiltonian, which is normal quantum dynamics, you want to push towards the ground state, and that's called quantum imaginary time evolution. Because if you stick an I in the usual equation for quantum time evolution, then you get the pushing towards the ground state instead of the precession. And the way they thought about doing this is to do a tomography. Using that tomography, figure out what gates push you closer to the ground state, then do another tomography, and then push closer. Yada yada yada. It's basically the same idea as quantum graph, but applied to a different application, and with therefore different ways you define how you're doing the gates in order to be useful for this different application. So we've got quantum graph, we've got QITE. both of them are showing us that this way of thinking where we take expectation values and manipulate expectation values is useful. It's useful for procedural content generation. It's useful for finding ground states. And it's different from the way we usually think in terms of I'll put a Hadamard here and a T gate there and a C naught over there. So can we combine these into a new model for quantum computation? Because we're used to thinking of the circuit model, but there's also the adiabatic model, there's also the measurement-based model. So like standard conventional computing has different models of computation, like the Turing model and the gate model. Could this be a new way of thinking about how to make quantum software, how to create algorithms? So we think the answer is yes, and we've called it the Motta model. Why have we called it the Motta model? Because one of the inspirations was Mario Motta with an A on the end, and Motta with an E on the end sounds like Motta with an A on the end. And also, you shouldn't name things after yourself in science, but we hope to sneakily get away with it by using the German for moth instead of the English. So we call it the Motta model, and it is just this basically the idea of you extract expectation values and you to keep a track on what the state is, and then you do gates by saying, I want that qubit to change its expectation values to this, and I want those two qubits to change their expectation values to that. And then under the hood, we always imagine that it's actually being run on the gate model. So really, it's just an interface for the gate model, and the interface figures out what gates it needs to apply in order to make that happen. But the Motta model is an interface that we can use to create new quantum algorithms. And my argument is that this is a better way. This is a way that you can think about creating quantum algorithms that you don't need a PhD in quantum computing for. This is something that we can contact game designers and say, do you want to do more PCG? Well, here's a paper that our guy wrote on how to do PCG with a quantum computer, and here's the same tool he used, and they can go off and design their own stuff because they don't need to understand the what a Hadamard does to a state vector. They just need to understand you've got this bag of variables, and here's how you tweak those variables. Go away and make some stuff. But what's important is that it is not just usable for people, but it also does quantum computing things. That it actually is an example of a proper quantum computer, a fully powerful quantum computer, and can be used for anything a quantum computer can do. Otherwise, you're just handing them a crippled interface. So you can check out the paper for the proof, but I think an overview of the proof is very simple. It is proof by hack. So it is, say you order the gate model quantum computer, and what turns up at your house is it's a Motta model quantum computer. So you can only control it through the Motta model interface. You're just wanting to do a Hadamard and then a CNOT gate, but you can't because it's all get block and set block and get relationship and set relationship. Is there a way to hack the Motta model device to be a gate model quantum computer? Because if you can, then it's obviously a fully fledged quantum computer. And what we find is that if we don't just give the user single qubit and two qubit expectation values, but three qubit expectation values, it's important that there has to be a limit because if we gave the user all expectation values, there is an exponential number of them, and that is too much. But if we give them only three qubit expectation values, there's still a finite number. And we find that if you've got a three qubit expectation value, three qubit expectation values for three qubits, then you have enough information to figure out. Yeah, let me try and explain this well. Okay, you've got three qubits. Let's call them one, two, and three. And you want to do a two qubit gate on two qubits. So what you do is you take the three qubit expectation values, and then you go away classically and figure out what would a C naught do to these three qubit expectation values. What would it how would it change them? How would it make them into new expectation values? And then you figure out what your new expectation values are after they've done the gate that you want to apply. And then you say, hey, multi-model quantum computer, here are my target expectation values. And then the multi-model quantum computer will go away and think to itself and say, the way I can make this happen is with a C naught. And then you've hacked it to doing what you want it to do. You have hacked it into doing a C naught without the ability to tell it directly to do a C naught. The reason why you need three qubit expectation values is because if you had two qubit expectation values, you would basically just be transforming the eigenstates of the two qubit density matrix that corresponds to those expectation values. And therefore, the phases on those eigenstates are undefined. So you would be doing something C naught like, but up to an arbitrary choice of phases on those eigenstates. Once you go to three qubits, you fix the gauge and you get exactly the gate you want. And this is important. It's important to note that this is regardless of tomographic noise. So even if your expectation values aren't perfect, um, it doesn't matter because the interface is just comparing the initial and the final and figuring out how to transform one to the other. So yes, this model is universal for BQP, although it is important to note this is not how we intend people to use it. It's just showing that it is fully featured. Okay, I'm going to run through another couple of things. While we were proving it, and while we were comparing it to QITE, we found that there are some things that quantum graph uh, does that aren't perfect and could be improved. So we're making a new version, the successor to quantum graph, incorporating everything we learned from the Motta model. It's called Quantum Drive. Also, we have another project called Mirror Quantum Awesomeness, which I'm not going to talk about now, but I encourage you to go and look at. But it is another way of doing intuitive benchmarking for at the device scale, and it's an adaptation of mirror randomized benchmarking. It's also game related, and you can actually use the levels of you can use our results from Mirror Quantum Awesomeness to make new levels of quantum backrooms, and they're pretty good levels as well. But this is basically what I wanted to tell you. We are a company that puts utility scale BQP complete tools in the hands of creative. You don't have to be an expert in quantum computing. All of this is powered by our platform, which is being released soon. Alpha access is extremely soon. If you want to make your own quantum creative things, come and sign up. And yeah, thanks for your attention. And if anyone's got any questions, please let me know.
Yes, thank you very much for the talk. It was very interesting. Um, are there any questions from the audience? Yeah, I can maybe start. So you at some point you were talking about in the map generate and game map generation about quantum advantage using QPUs. What do you mean by advantage there? I mean, it's a game you're making. Is the advantage in the game
Yeah.
being more fun, or what do you mean there by advantage?
Yeah. So, well, the fact that it is more vaguely defined is helpful because people aren't really searching for an advantage. They're just searching for something that they find useful. So if someone makes a level or finds a way of making levels that their players really enjoy, that's the advantage. And if they found a
Hmm.
way to do it with a quantum computer rather than a classical computer, that's great. I think as time we're every part of quantum computing is in this arms race with the
Hmm.
classical. I mean, we saw recently IBM come along and say, "Look at our doped T-gate experiment. We've got a quantum advantage." And then a couple of weeks later, someone says, "Nope, we did it."
Hmm.
So I think we'll. we're always wanting to push the envelope about how sophisticated you can be with a QPU in the creative space. And so we will make a tool,
Hmm.
people will find it useful, then and then hopefully we nerd snipe the tensor network guys and they come along and say, look, actually we can do it without a QPU, but we
Hmm.
don't care because we're already on to the next cool thing
Yeah.
and then the next cool thing and then the next cool thing. And at some point it will come that you can't do it classically anymore. And the the idea that we can look forward towards an era in which we have these optimization constraint satisfiability tools that are solving computationally hard problems is the motivation for the fact that it is going to get there. But we are not a quantum advantage claim hype sort of a company.
Hmm.
We're just being useful to creative sort of a company.
Yeah. Yeah. You were also talking about using these games as a quantum benchmark for devices,
Hmm.
like building levels with a QPU and then seeing what the reactions are, and then that would be a metric for how good the QPU is. It's a bit of a creative metric, but that could
Yeah.
be very
Yeah, I
interesting.
didn't really talk about the quantum awesomeness stuff, but quantum awesomeness was a project I did. I started back in 2017, and it was a decent benchmarking project for 2017, but it's not up to 2020 standards where you need to be like doing randomized benchmarking and things like that. So we gave it an upgrade, and it is both a variant of device-wide randomized benchmarking. So it gives you good concrete data on how your quantum computer is doing, but also you can make the levels into a puzzle game so that while you, the quantum scientist, are able to understand how well the device is doing, so can your dad, the
Hmm.
retired um, supermarket worker, in my
Hmm.
case.
Are there questions from the audience? I had one more technical question actually. So this
Oh,
multimodal stuff, where
yeah.
you use expectation values to drive the algorithm to the desired state, let's say, and this emulation overhead. Have you done like for specific algorithms like the quantum Fourier transform, how that description would be like in this multimodal?
Yeah,
Or
so
if it
it's
would be
essentially just the
simpler
same
or
list of gates, but you just have to use this little hack of figuring
yeah,
out how to
yeah.
transform.
So I realized that the result would be the quantum Fourier transform. But I'm
Yeah.
curious about the steps of picking the expectation values. That would be a
Yeah,
different
so this is
description of
why
the
there is
program.
a complexity overhead because every time you do a
Hmm.
gate, or at least
Hmm.
a depth of gates, you have to do a tomography.
Hmm.
You have to look at the tomography. So it does mean rather than doing gate, it's gate, tomography, add another gate onto the circuit. So run the circuit again until that point.
Hmm.
Tomography, add another gate, run the gate circuit until that point. So yes, absolutely, there's a polynomial overhead in hacking it to be a gate model quantum computer. So
Hmm.
if you are delivered the wrong quantum computer, you probably should complain and return it rather.
Hmm.
But again, that's not well, that is an inherent overhead in using this interface.
Yeah.
Well, and
Okay.
someone did ask, could someone use this for random number generation? Yes. In fact, but I wouldn't encourage them to. And in fact, we've got someone from the games, like a game designer right now using it. And he immediately realized he could use it to make a random number generator. And he re immediately realized that that wasn't the best use of it.
Hmm.
So I was very encouraged by that. Because what I find, one of the motivations for all this actually was going to quantum game jams, quantum hackathons, people with no background in quantum thinking, I'm going to make a game. and then them just discovering, oh, I can do a Hadamard and then a measurement, and then it's a random number generator, and then doing whatever they want. In fact, I went to
Hmm.
a game jam where there was some of the guys who created Angry Birds, and they were given a simulation of a Bose-Einstein condensate to make a game out of. And some people made cool games where you're surfing on the wave function, and these guys just thought, oh yeah, we can use that to make a random number generator, and then just did are you plugging your USB into in the right way round? So that to me is, I mean, they were nice guys, but the wrong path to take when making a quantum game, and you should be surfing the wave function instead.
Hmm. Cool, cool. Um, yeah, I guess if there are no other questions, yeah, thanks again. It was a really fun talk.
Great, thank you.
Um,
All right,
okay.
see you all on the Discord then, both the
Yes,
Unitary Foundation one and the Moth one.
exactly. Okay, thanks.
Thanks.
Bye
Bye
bye.
bye.